questions like these, we need the 3 standard rules for logs, which we'll have another look at later. But they are that the log base a of x plus the log base a of y is equal to the log base a of x times y. Log base a of x minus log base a of y equals log base a of x divided by y. And n times the log base a of x is equal to log base a of x to the power of n. So these are the tools we have to deal with this question. So if we start off by just writing the question down, we have 2 log base 10 of x equals 1 plus log base 10 of 5 take away log base 10 of 2. And there are various different ways of tackling this, but one way of doing it is to turn the 1 into a log. So that means thinking about what log means. So log base a of x means what power of a will give us x. So if we think of 1 being some sort of log, so we have log base 10 of something is 1. If we put x in there, so we're going to work out what x must be. So log base 10 of x means what power of 10 will give us x, and the power of 10 that will give us x in this case is 1. So what this means is 10 to the power of 1 must be x, and that means that x is 10. So in our question we can replace the 1 by log base 10 of 10, and then we'll write the rest of it out. And now we'll use our rules. So on the left hand side we have a case of this rule. So we have something times a log, and so that will change into log base 10 of x to the power of 2. On the right hand side we have an add here, so we're going to use that rule for that, and we have a takeaway here, which means we're going to use that rule. So we can combine these 3 logs into log base 10 of the first 2 multiplied together because they're an add, so that's 10 times 5, and then we would divide by the 2 because that's a minus log. So this gives us log base 10 of 10 fives are 50, divided by 2 is 25. And here, then, we don't need to write this down, but what we're going to do is do 10 to the power of log base 10 of x squared is equal to 10 to the power of log base 10 of 25. And 10 to the power of log base 10 cancels out, so that leaves us with x squared equals 25. That means that we have x equals 5 or minus 5. And it's very important to always, when you're square rooting, consider both of the answers, the positive and the negative. In this case, we can't use the minus 5 because in the question it says log base 10 of x. Now that would mean if it were minus 5 we'd have log base 10 of minus 5, and at this stage you're not allowed to do logs of negative numbers. It is in fact possible to do logs of negative numbers, but we don't deal with that yet. Okay, so we have for part A. I'd like to mention here as well a good technique for exams, which is when you have a numerical answer that comes from an equation, you just write CH, perhaps in pencil, and then if you have time left at the end of the exam, you can check your answer in the calculator. So for this question, we could put 2 log base 10 of 5 into the calculator, find out what it is. I'm not going to bother doing that. And then you could do 1 plus log base 10 of 5 plus, minus log base 10 of 2. And if they're both the same, then chances are you've done the question correctly. For part B, we have 3 equals 2e to the 0.5x. And so the first thing we will do is divide both sides by 2 to get the e to the 0.5x on its own. And I'm going to turn it round, so that will give us e to the 0.5x equals 3 over 2. And now the inverse of e to the power is log, as in ln, and although it's written ln, we still say log. It's in fact the natural log. So we can take ln of both sides, and often people wouldn't write this, but what we're doing is ln of 0.5x, so log of 0.5x equals log of 3 over 2. What we generally just write is that 0.5x is equal to log of 3 over 2. And that means that x is 2 times log of 3 over 2, times in both sides by 2. And then we ought to be able to leave our answer as that, because that's an exact answer. But since the question doesn't tell us whether we need a numerical answer or not, we better use our calculators to produce one, and that would be 0.81093, and there's no clarity on how many decimal places to do, so you could leave it at that or do fewer decimal places. Okay, now for part C, well, the first thing to do is to think of where this y equals 2 to the x comes in. And the expression that we're meant to deal with is 4 to the x minus 10 times 2 to the x. So the 10 times 2 to the x, that's okay, that's going to be 10 times y. But we need to think about what the connection is between y equals 2 to the x and the 4 to the x in the question. And what we can say is that 4 to the x is the same as 2 to the power of 2 to the power of x, and that's the same as 2 to the power of 2x, thinking of indices rules, and that is the same as 2 to the x to the 2, so finally that gives us that 4 to the x is going to be y squared. So our expression 4 to the x minus 10 times 2 to the x is actually going to be y squared, take away 10 times y. Now, hence solve the equation, well, that means that the left-hand side of this equation is what we've just expressed the original as. So we can now write y squared minus 10y equals minus 16, and we have a quadratic. So we can say y squared minus 10y, adding 16 to both sides, is 0. And then we think about how 16 splits into factors, because the final term in the quadratic will be two numbers multiplied, and we have a minus for the y term, and because the minus 10 is these whichever pair we need added, they need to be negative, because The final term is positive, so we have to have a minus times a minus or a plus times a plus. The middle term is negative, so they both have to be negative, and we can see that minus 2 and minus 8 does the trick. So that gives us y minus 2 times y minus 8 is 0, which tells us that y is 2 or that y is 8. Now, we actually have to solve it with an x value, but we know what y is equal to. It's equal to 2 to the x, so we can say 2 to the x equals 2 or 2 to the x equals 8. And then you can probably see that for the first one we need x to be 1 because any number to the power of 1 is itself. And for the second one you probably know that 2 cubed equals 8, so that tells us that x is 3. Of course, these two, although we can spot the answers and we wouldn't faff about using a calculator or anything in it, or any other technique in the exam, in fact we can use logs to solve these. So because they're 2 to the power, we would use log base 2. So we could say that log base 2 of 2 to the x equals log base 2 of 8. That means x equals log base 2 of 8 because the log base 2 and the 2 to the power cancel each other. And then we can think about what log means. So log base 2 of 8 means what power of 2 gives us 8, and of course that's 3. So that's just a thing to think about. In this question, it's worth having a quick look at the mark scheme version of the answer, which demonstrates that there are always different ways of doing questions. And in fact, in the mark scheme, they have done a more standard approach, which is to get all the logs on one side and then use the rules to combine them. So in this first line here, they've done what we did with moving the 2 up using that rule, and they've moved the logs onto the left hand side. And in the second line they've combined these 3 again in the same way as we did. Obviously it looks slightly different because it's got the x squared bit in it now, so that's in this line. And then they've done 10 to the power of both sides. And of course 10 to the power of log base 10 of a number is that number. So and then on the right hand side we've got 10 to the power of 1, which is of course 10. And then they've finished off with basic algebra. This is a good point to mention about the fact that we do at this point get the minus 5 as a possible solution, and I talked about this in the solution we've just looked at before. Turns out that you can have logs of negative numbers, and this relates to a very famous mathematical identity, which is Euler's formula, which is e to the I pi plus 1 equals 0. Of course, in part B we deal with e, the natural exponent, and then log, spelt ln, the natural logarithm. But if we look what we can do with Euler's formula, we can express it as e to the I pi equals minus 1. And then if we take logs of both sides, we get I pi equals log of minus 1. Now, what that means is that if we do want to find the log of minus 5, and I'm not going to bother going into log base 10 because that's just another complication, but if we wanted the natural log of minus 5, what we can do is recognise that we have minus 1 times 5, which we can then use the log rules to separate that off as log minus 1 plus log 5, and this then gives us I pi plus log of 5. Now, unless you do further maths, you won't have come across I, and I is in fact the square root of -1, and this leads to complex numbers. This is certainly taking us beyond Maths A level, but some of you will be going into Year 13 and having a go at further Maths AS, and many of you may be going on to Maths or Engineering or other degrees which will use complex numbers, so this is just a tiny little taste of that. The second solution given in the mark scheme for Part A, I'm afraid I don't like very much, because it's using a calculator straight away, and it happens that on this occasion we do end up on the calculator with the exact answer 5, but for a mathematician it's unsatisfying, because we've had to use a calculator, or we could have used log tables as people did before calculators, but also we are risking introducing inaccuracy. And in fact, on some earlier calculators, we may well have ended up with something like x equals 4.99 something, or 5.001 something. And in fact, by doing it in a more mathematical way, as we did in my version of the answer and in this part of the mark scheme, then you get the exact answer. Now, very often there are questions on the log proofs, and these are useful anyway in one's understanding of logs. So if we write down the three identities that we have that log base A of x, y, equals log base A of x plus log base A of y. We have log base A of x over y equals log base A of x minus log base A of y, and we have log base A of x to the n equals n log base A of x. Now, for those of you who struggle with this, the first thing to remember is that what the proof relies on is moving into an area that you are already hopefully comfortable with, which is indices. And so, bearing that in mind, the first thing we do is that we convert all the terms on the right hand sides, and it's the same for each of the proofs. I should have put an equal sign there. Of course, for the last one we only need the p term. And now, bearing in mind that log base A of x means what power of A gives me x. So for this first one, the power of A that gives me x is p. So the power of A that gives me x is p. The power of A that gives me y is q. And again, this works for all of the proofs. Okay, so once we've done that, we then start off with looking at x, y in this one. We look at x over y in this one. And we look at x to the power of n in this one. So now we've converted into these forms, then our x is now equal to a to the p, and our y is equal to a to the q. And here we have a to the p over a to the q, and here we have a to the p to the n. And then, and this is the point, because we've moved into indices, we know the rules here. When we multiply two numbers with indices that are multiplied together, we add the indices. When we divide, we subtract the indices, and when we go to the power of n, we can multiply the indices. So, having gone into indices, we then come back into logs. So, we take log base a of xy. Now, log base a of a to the power, they cancel each other out, so we now have p plus q here. Here we have log base a of x over y, and we have p minus q. And here we have log base a of x to the n, and we have np. And now all that remains is to go back to this line and replace our p's and q's. And of course we must always mind our p's and q's, children. So we have log base a of x plus log base a of y. Here we have log base a of x minus log base a of y. And here we have n times log base a of x. And so we can summarise the process here by saying that first of all we move to indices. Secondly, we use the indices rules. And finally, we move back to logs.
Useful with logs to have an idea of the shape of the log curve. You sometimes might have to draw it anyway, and it can be difficult to remember. So just like with the proofs where we went into indices, which was a familiar topic, then for looking at the log graphs it's worth looking at exponential graphs. They are the inverse of the log, so we can get the shape of the log by looking at them. So the advantage there as well is that you've come across exponential graphs in mathematics. You may well have come across them in, say, geography with something like population growth, and in, say, biology with bacterial growth. So they're relatively familiar. And here we can see we have 10 to the power of x, and that 10 is actually related to this slider, so we can change that in a minute if we want. Okay, so we know that the log is the reflection of this in the y equals x line. So if we pop that in, and then we can have a look at the log curve as well. And if you tilt your head 45 degrees to the right, or tilt your screen for that matter 45 degrees to the left, then you will see that that's a beautiful reflection. Okay, notice as well, we were talking about log of 5 and log of minus 5 earlier on. The log graph on the real plane, so this is with real numbers, doesn't appear in this quadrant here. And one way of thinking of that is that the exponential curve doesn't appear. It doesn't give us negative values of y when we raise numbers to the power of x. So that's one way of remembering about that. We can also, as I said, we can move the slider. Now if we slide this down, the blue curve, the exponential curve, moves to the right because we have a smaller number raising the power of x. And so actually, although it looks like it's moving to the right, in a sense what's happening is the values are moving downwards because they're getting lower. As the base for the log curve gets smaller, then we need a greater value of y to raise the power up, so the log curve rises. And that's the end.